Hello, welcome to this webinar on the realities of topology optimization. My name is Dave Hayden and I'm a Senior Engineering Consultant for Blueprint. Blueprint is a strategic consultancy focused on additive manufacturing. We have 15 years experience in nearly every industry imaginable and across all AM technologies. Our goal is to help customers make sense of 3D printing. If only life were as simple as pushing a button, we could load the original CAD design of our part into a Topop program, like the picture on the left here, punch in a few parameters and boundary conditions, playfully jab at the big red Go button, and a few seconds later, a printed part falls out of the machine, like the one on the right. Some flashy futurists might have you believe that this is the case, but actually for the rest of us firmly grounded in the world of engineering, we know that there's a little bit more to it than that. In this webinar, we're going to follow the journey of this part through a topology optimization process. So to get started, I better tell you what it is. It's actually a box for a set of circuit boards that are used for a control system on a rocket. And the designers wanted to see if they could improve on the existing design to reduce its weight as well as increase its stiffness. Here we have a much more realistic representation of all the major steps you'll need to go through to get yourself from the initial or traditional part design to the manufactured and optimized part. Over the next few slides, we'll go through each in turn. And it's worth noting that like all optimization tasks, this isn't necessarily a linear process. The Topop software does some streamlining for us, but there's still often the need to review the results, tweak some parameters, and rerun the optimization algorithm to see if the first attempt can be improved. Before we go any further, however, we should start this story with a brief look at quality control and certification, because for many industries, without this, no matter how optimized your design, if you don't have this kind of documentation, you're going nowhere. Industries such as aerospace, the space sector, or the railways are quite rightly extremely tightly regulated in their operational processes to protect the people trusting them with their lives. If this is the kind of world you work in, certification or quality control considerations is something you should consider right from the start. Being prepared like this and having early conversations with regulatory bodies when exploring new technologies, like additive, ensures that there are no nasty surprises for anybody in regulation when you come to deploy the final part. And whilst additive is a newer technology compared to many traditional ones, companies like Stratasys are offering materials which meet fire and smoke specifications, as well as packages that provide you with statistically reliable allowables data and quality documentation. This means you have mechanical data to design with, and material and process documents that enable additive to integrate fully into your quality management system. This keeps your quality high and keeps the regulatory bodies satisfied that you are delivering repeatable parts. So this leads us on to the next stage, finding a business driver. Just because we can do something doesn't always mean we should. And before we go into any technical discussion, I want to nail down a solid business case for why we are even talking about this topic. Essentially, why would we put all of this effort into redesigning a part to be lighter, stiffer, or smaller just because we can? There needs to be some kind of performance or financial-based benefit to the business for us to invest all of this energy in this activity. The space industry is a great example of this because weight is very important. It takes so much energy and auxiliary hardware to put a useful object into space. There is a very extreme ratio between the parasitic mass of a rocket, fuel, engines, tanks, superstructure, and actually the useful payload that we want to put up there, the satellite. With the cost of launching a rocket so high and the amount of useful payload space available on each rocket so low, we see the cost of around 1 kilogram being 20,000 euros per launch, which means that weight savings equal big financial savings. In the motorsport industry, weight is also important, but we can see things from a different perspective as well, because it's also worth considering that topology optimization can be used to optimize other parameters besides weight. For example, to maximize stiffness in the suspension system, or to reduce component size in tight areas. In this case, essentially, customers and racing teams are prepared to pay to go faster. So we have a link here between weight and performance, and ultimately between performance and money. We see that in the motorsports industry, the value of a kilo is between 100 and 1,000 euros. And finally, in aerospace, we can readily draw the argument again from first principles. Much like rocket launches, to get a payload, in this case passengers and their belongings, into the air, it requires parasitic mass, fuel, seats, entertainment systems, etc. And if we can reduce this parasitic mass per kilo over the lifespan of an aircraft, we can look to save between 10 and 100 euros. Now that we've established a business case, we can actually start to look into the technical side of doing top-op or topology optimization. The first thing we have to do before running any kind of optimization is tell the software what constraints to work within. A design space is declared to prevent the code from trying to model outside of this envelope, and this ensures that the final design won't interfere with any other parts, for example bolts or other pieces of the assembly. This space is shown here in green. Next, shown here in red, we've also modelled in areas that must be included in the final design and cannot be optimised. For example, the connection points for any fasteners must stay as they are, and the plug sockets for the circuit boards need to exactly retain their shape. Now, much like a regular FEA simulation, we define the loads we expect the component to have to withstand, as well as the constraints keeping it in place, shown here with the various arrows. Next, we need to define the material and its mechanical properties. It's worth thinking about a factor of safety here as well, if you haven't already accounted for this. One thing worth considering is few topology optimization codes are able to cope with anisotropic materials. The unfortunate thing being that almost all AM materials are at least slightly anisotropic. So when defining your material, consider how to approach this. The obvious common fix is to use the lowest material properties, often in the z-axis, as the global isotropic properties for the simulation. Finally, as top-op programs become more advanced, we're seeing the option for the user to be able to set rules or preferences on how the program should optimize the part. Things to consider here are that whilst it might be lighter to design a complex organic-looking structure, these may be very heavy on support material usage when it comes to printing. So you might want to prevent the program from creating overhanging structures where possible by setting a rule that the program should preferentially create structures that do not overhang. Likewise, some codes can be programmed to appreciate that creating structures in the z-axis could be much more costly than printing flatter parts predominantly grown in the x or y-axis. Now that we've initialized the program, we can run the simulation. However, because of the iterative nature of topology optimization, simulations can take some time. The program is essentially running an FEA simulation, making small adjustments to the model geometry to remove areas with high stresses or deflections, and then rerunning the simulation to see if there was an improvement over the previous result. We're talking hours rather than days, but this is still something you just have to wait for. At the end of the simulation, you'll be able to review the results and make some adjustments to your parameters, or perhaps try a different loading case, so expect to go through this cycle at least a couple of times. After a few hours of waiting, we finally get to review the results of our simulation, and we can see that the results are kind of, well, messy. Now, this definitely isn't something that we should just go and print directly. However, if you think of topology optimization more as inspiration for how to design the component, they provide a very valuable insight into where material is and isn't needed, and we can always clean up the design later. At this step, we should consider if the results we are seeing are sensible based on the boundary conditions we chose. And we should also check if the results going forwards are still going to be manufacturable. Additive manufacturing is very flexible, but it can't manufacture literally everything. There are still some guidelines and hard limits. For example, some processes might require large amounts of support material to produce these complicated structures, which can in itself be quite expensive or time-consuming to remove. So try and plan for the final manufacturing scenario to ensure that the cost and lead time benefits you're gaining in these stages aren't lost later on by other negatives. Other things that are worth considering include if the top-op design has very thin wall thicknesses or extremely thin wire-like struts. Even if we could print these, will they survive the operational environment of the finished part? Maybe we should thicken these up later on. And finally, just like a regular FEA simulation, it's important to consider a range of load cases to produce a balanced design, as unfortunately it's quite rare that a component is operated under such a pure single load case, so we might need to repeat this simulation for some others. From the results on the previous slide, we now have a good idea of how much weight we might be able to save over the original design. This means that we can infer if there are any financial savings or revenue opportunities as a result of this redesign activity. As I mentioned before, in aerospace or space industries, we can equate a weight saving to a fuel or launch cost saving, whereas as industries such as motorsports, a weight saving or an increase in stiffness manifests itself as a performance advantage that the market is willing to pay for. The consulting team, we do a lot of economic modelling on AM parts, which enables us to predict what a freshly designed top-op component might cost to manufacture. Now, if we subtract these costs and find that we're still looking at sensible figures, then we know this whole exercise is worth considering. And that's why we're doing this economic analysis so early in the process. If we're able to pass this economic stage gate of the previous slide, then we can carry on with the technical work again. As I mentioned earlier, the results of the topology optimization simulation are often a bit weird. Mostly this is because in order for the iterative top-op simulation to run quickly, the mesh used is very coarse, and with these designs being computer generated, it's understandable that the odd illogical result might occur without a human in the design process. We should consider, can we easily manufacture the shape the top-op simulation has produced, or would it even be practical to use? Its shape might make it difficult to hold, or it might be prone to collecting dirt, grease and grime inside of its complicated structure. In this CAD reconstruction and smoothing step, we can add back in the human designer. We can redraw the results of the top-op simulation into a more logical design and smooth out those lumps and bumps caused by that coarse mess. Now we have a CAD reconstruction with some light human input, it's a sensible time for us to check our work with a much more detailed traditional FEA simulation. The initial top-op software we ran to optimize our geometry was a simulation, but as I explained before, quite a low resolution or fidelity simulation. By using a much refined mesh, we can ensure there aren't any small stress raisers or areas prone to failure that the previous top-op simulation might have missed, and especially given the fact the design we are now working with was altered by us in the previous stage. Other reasons for this step might include that you may want to do some more complicated multi-physics simulation or see how your component performs under dynamic loading. So assuming that we have a final and stress-checked design, it's time to move on to the manufacturing phase. No 3D printer works directly from CAD data. They all employ some type of CAD-CAM process that translates this 3D data into a series of 2D slices or toolpath instructions. And this is actually a good thing. Whilst you could just take some default parameters and print seemingly directly from a 3D CAD file, taking an interest in your slicing and printer setup will always give you a higher quality result. And this is because it's possible to adjust many different parameters. For example, to improve surface finish, part porosity and tensile strength, you can adjust print orientation, layer height and tip size. Now we have a set of slice or toolpath data which the 3D printer can work from. These can be loaded into the machine or scheduled into the print queue over the network. Depending on how the machine was left following the previous job, it may need us to load fresh material or different material and prepare a clean surface on the build plate. Generally, on an industrial system, once the printing process itself has started, it requires no further interaction until the job is finished, where human hands are once again required to remove the part from the machine. It's rare that parts straight off the machine can be directly put into service, especially in high-performance engineering applications, as there's normally one or two post-processing steps that are required to improve part performance or achieve those tight tolerances. For example, any support material must be removed. Generally, the high-performance polymers only have breakaway support material, not soluble because of the high temperatures involved in printing them. Additively manufactured parts generally have rougher surface finishes than traditional methods, so if surface finish is important, manual sanding or automated vibratory polishing might be required, especially on mating or sliding surfaces. Where precision is required, it's wise to have holes reamed or bored to improve the accuracy of their final size and positioning, as well as a general rule of thumb where threads are needed, these holes might need to be tapped or inserted with brass bushings post-printing. Well, congratulations, you made it. We've gone through all the stages in the circle of top-op, right the way through to the other end. If you're still interested and you've got further questions, I've put some links on the screen here where you can do a bit of further reading. I'd like to thank you for listening. It's been my pleasure to walk you through some of the details of how to go about using topology optimization in the real world. It's an amazingly powerful tool for high-value engineering, but as we've learnt, there is a little more to it than you might first have imagined. If you'd like to carry on our conversation, I'd love for you to contact us at hello@additiveblueprint.com, and we can take things from there. I've been Dave Hayden from Blueprint, and thank you very much once again for listening to our webinar.